Section 3.3, Arc Length and Curvature. Your homework for this section are problems 103, 105, 117, and 121. In this section, we study formulas related to curves in both 2 and 3 dimensions and see how they're related to various properties of the same curve. For example, suppose a vector value function describes the motion of a particle in space. We would like to determine how far the particle has traveled over a given time interval, which can be described by the arc length of the path it follows. Or suppose that a vector value function describes a road we are building, and we want to determine how sharply the road curves at a given point. This is described by the curvature of a function at that point. We explore each of these concepts in this section. Let's begin with the arc length of a vector value function. Theorem 3.4 Arc length formulas. For a plane curve, given a smooth curve C defined by the function r of t equals f of ti plus g of tj, where t lies within the interval ab, the arc length of C over the interval is s is equal to the integral of b over a of the square root of f prime of t squared plus g prime of t squared dt. It can also be defined as the integral over b over a of the magnitude of r prime of t. And it would also similarly apply to three dimensions space curve. Given the smooth curve C defined by the function r of t equals f of ti plus g of tj plus h of tk, where t lies within the interval ab, the arc length of C over the integral is s is equal to the integral of b over a of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. Let's do an example. Example A is fairly easy. So our example reads, calculate the arc length of each of the following vectors, or each of the following vector valued functions. For A, we have r of t equals 3t minus 2i plus 4t plus 5j over the interval, the closed interval of 1 and 5. So according to our definition, we're going to use that interval, apply the integral of the magnitude of the derivative. So let's go ahead and take the derivative. So that we have r prime of t is equal to 3i plus 4j. So I just took the derivative of each argument in I and j. Then we apply the derivative. So our definition is the integral of 5 over 1 of the square root of 3 squared plus 4 squared dt. This is not so bad. We don't have a variable to work with. We're working with constants. So we take the square root of 3 squared plus 4 squared, which gives us 25. So I'm taking the integral of 5 dt, which just gives us 5t. And then when I plug in 5 and 1, we get 25 minus 5. So our answer is 20. The other one's a bit more involved. So let's take a look at example B. R of t equals t cosine t plus t sine t and 2t of the interval t between 0 and 2 pi. Well, let's begin by finding the interval. So our integral is r prime of t, which is equal to, well, as we look at our first term, we have two arguments of t, right? So we have to do product rule. So that we have r prime of t is equal to cosine of t, since we have a derivative of 1, of t, which is just 1, and then we have minus t sine of t. It should be a plus, but because the derivative of cosine is negative sine, we carry the negative over. And then we have the same thing here, so we have to also do product rule there. so that we have sine of t, since the derivative of t is 1, plus t cosine t, since the derivative of sine is cosine. And then the derivative of 2t is just 2. So there we have our derivative for r. Okay, let's take the integral from 2 pi to 0 of our derivative squared, with each component squared as well. So that I have cosine of t minus t sine of t squared plus sine of t plus t cosine of t squared plus 2 squared dt. Okay, well, let's expand it. Let's hope some things cancel out. So if we square that first term, if we square this, we're left with cosine squared t minus 2 cosine t times sine t. And then for our next term squared, we have plus sine. We're not done with that first binomial. So then we have plus t squared sine squared t. There we go. Let's continue with the next one squared. We get plus sine squared t plus 2 sine t times t cosine t. And then writing that dot between cosine and t to show multiplication. Plus t squared cosine t squared. And then lastly, we have plus 4. That's messy. Luckily, things do add up to make 0. So we have this 2 cosine t sine t and this 2 sine t cosine. While they're being multiplied in different order, we know order doesn't matter for multiplication. I have a positive and a negative. Those add to make 0. And then we have Pythagorean theorem rule. Cosine squared plus sine squared, that equals 1. So we can replace those two together with 1. So that we now have, let me write that so that you can follow. Cosine squared t plus sine squared t equals 1. That's our Pythagorean identity. This one should be your best friend by now, right? Okay, so then we are left with 2 pi to 0 of the square root of t squared sine squared t plus t squared cosine squared t plus 4, and then this is 1, right? So don't forget that 1. Now notice that if we factor t squared, we again have Pythagorean identity. T squared times sine squared t plus cosine squared t, we again get 1. So that we have the integral of 2 pi to 0 of, so we have t squared times 1, which is just t squared, plus 5. Okay, this is not a pretty integral, and actually it's one of those integrals that you would use like an integral chart to figure out. So think back to like your calculus book, you had some page where it has all these funny integrals. This is one of them. So it's not something you can do with just u substitution. All right, so our integral rule for this one, our integration formula, is the integral of the square root of u squared plus a squared du is u over 2 times the square root of u squared plus a squared over 2 ln of the absolute value of u plus the square root of u squared plus a squared plus c. Okay, so let's apply this to our formula. So if you apply that to what we have for our situation, we're left with the integral from 2 pi to 0 of t over 2 of the square root of t squared plus 5 over 2 ln of the absolute value of t plus the square root of t plus 5. Well, that's our integral, right? So we don't have to write that anymore. All right, let's clean it up. We're applying this from 2 pi to 0 so that we have 1/2 times 2 pi of the square root of 2 pi squared plus 5 ln of 2 pi plus the square root of 2 pi plus 5 minus 1/2, and stuff cleans up so that we're just left with 0 plus 5 ln of the square root of 5. Okay, so in the end, we work this out a bit more. We clean up the inside, so we have 1/2 2 pi square root of 4 pi squared plus 5 plus 5 ln of 2 pi plus the square root of 2 pi minus 5 plus, and then we have the 5 that we can factor over, so 5 over 2 ln square root of 5. And that was always a minus. Okay, now we're left to punch this into our calculators. Okay, so that we get at the end, we should get about 25.343. Well, that was really long. Arc length parameterization. We now have the formula for arc length of a curve defined by a vectored value function. Let's take this one step further and examine what the arc length function is. If a vectored value function represents the position of a particle in space as a function of time, then the arc length function measures how far the particle travels as a function of time. And we have our definition for arc length. Theorem 3.5 arc length function. R of t describes a smooth curve for t greater or equal to a, then the arc length function is given by s of t is equal to the integral of t to a of the magnitude of r prime du. Furthermore, ds dt is equal to the magnitude of r prime t greater than 0. If r prime of t is equal to 1 for all t greater than a, then the parameter represents the arc length from a starting point, whatever value we're working t equals a. All right, find the arc length parameterization for each of the following curves. Let's take a look at this example A. So according to our definition above, if I want to find the arc length, I have to take the derivative and apply that magnitude rule to the derivative as you apply the integral. So r prime of t is equal to negative 4 sine of t, since derivative of cosine is negative sine, I plus 4 cosine of t j. Let's apply the integral from t to 0. So that we have the integral from t to 0 of the square root of negative 4 sine of u squared plus 4 cosine of u squared du. Okay, let's go ahead and clean it up. This one's not so bad. So 4 squared is 16. We're left with 16 sine squared u plus 16 cosine squared u du. We can use Pythagorean identity so that we're left with, well, if you factor that, we see that sine squared plus cosine squared gives us 0, so we're just left with 16. So we're left with the square root of 16, which gives us 4. We apply the derivative, so we're left with 4t, not derivative, the integral, 4t from t to 0, which just in return gives us 4t. But remember, we have to rewrite our argument in terms of whatever we're working with. So we want an s, but we're given t. So we have that this s is equal to 4t, which is what we came up with. Let's write it in terms of t. So divide by 4 to both sides, we're left with s over 4. So now we can apply that to our function r of t. So that we have r of t is equal to 4 cosine. T will have s over 4, I plus 4 sine s over 4, j. And we have to change our argument when s over 4 is greater than 0 and s is greater than 0. Let's take a look at example B. Again, we want to apply the derivative so that we have r prime of t is equal to 1, 2, 2. Okay, let's go ahead and apply the integral from t to 3. So we have t to 3 of the square root of 1 squared plus 2 squared plus 4 squared. Alright, that gives us the square root of 9 du. Let's go ahead and apply the integral so that we have 3t. The square root of 9 is 3, so we have 3t from t to 3, so that we're left with 3t minus 9. We do the same as before. We set it equal to s and solve for t. S is equal to 3t minus 9. In return, we get t is equal to s minus 9 over 3. You can clean it up to have s over 3 plus 3, if you like. Okay, let's input this into our function, our vector valued function. So we have r of s, not t, r of s is equal to, t is now s over 3 plus 3. So I have s over 3 plus 3 plus 3, 2 times s over 3 plus 3 minus 4. We're using this, right? And then next we have 2t. So we have 2 times s over 3 plus 3. All right. And again, we change our values. When s minus 9 over 3 is greater than 3, and s is greater than 0. Curvature. An important topic related to arc length is curvature. The concept of curvature provides a way to measure how sharply a smooth curve turns. A circle has a constant curvature. The smaller the radius of the circle, the greater the curvature. You see how you have a really steep curve right here, and it has a small circle, whereas this here you have a very wide curve and you have a wider circle. Definition of curvature. Let C be a smooth curve in a plane or in space given R of S, where S is the arc length parameter. The curvature K at S is K is equal to the magnitude of dTds which is the same as the magnitude of T prime of S. So we're going to learn some alternative formulas, which are actually more helpful than that first one. So we have 3.6. Alternative formulas for curvature. Let C be a smooth curve given by R of T. Then the curvature K at C is given by K is equal to the magnitude of T prime of T divided by the magnitude of R prime of T. So that's one way. You can also find the curvature. If C is a three-dimensional curve, then the curvature can be written by the formula of the magnitude of R prime of T cross product R double prime of T divided by R prime of T cubed. A third one is if C is a graph of a function and y equals f of x, and both y prime and y double prime exist, then the curvature K at point x comma y is given by K is equal to the absolute value of y double prime divided by 1 plus y prime squared, all of which is raised to the 3/2 power. Okay, let's go ahead and take a look at an example. Find the curvature for each of the following curves at a given point. Well, we have to use some of what we know, which is that tangent curve, and then we can apply that curvature formula that we learned. So this first example reads, find the curvature of each of the following curves at a given point. So that we have 4 cosine ti plus 4 sine tj plus 3. I have on my notes, this should have been a 3t. 3tk. And we want to evaluate at t equals 4 pi over 3. Okay, well first we need to find that t of t, which is made up of r prime of t divided by the magnitude of r prime of t. So that's going to be your first step. And then once we find that value, then I can use one of our formulas above. We can actually use that first one, where k is equal to the magnitude of t prime of t divided by the magnitude of r prime of t. Okay, let's find that first formula. So we need to find the derivative. R prime of t is given by -4 sine t I plus 4 cosine tj plus 3k. Okay, so first we want to apply this formula so that we have t of t is equal to -4 sine of t, 4 cosine t, and 3 divided by the square root of -4 sine of t squared plus 4 cosine squared t plus 3 squared. Again, we use a Pythagorean identity so that we're just left with 16 for this value here. And we're left with -4 cosine t and 4 cosine t and 3 divided by 5. Since that denominator ended up being 4 squared plus 3 squared under square root. All right, so what do we get? We have negative 4 over 5 sine of t divided by 4 over 5 cosine of t of 3 over 5. Alrighty, so that is our t of t. That's our answer. We're going to use that to find our curvature, which is made up of t prime of t divided by r prime of t. Okay, so now to calculate t prime of t. Okay, let's take the derivative. We're left with negative 4 over 5, the derivative of cosine of sine is cosine t, and then negative 4 over 5 sine t. Derivative of a constant is 0. Okay, now I can apply my new formula. K is equal to the magnitude of t prime of t divided by r prime of t. Okay, so that we have the square root of negative 4 over 5 cosine of t squared plus negative 4 over 5 sine of t squared plus 0 divided by the square root of negative 4 sine of t squared plus 4 cosine of t squared plus 3 squared. It's not so bad, it's just a lot of repetition, right? Okay, so we clean it up and evaluate at t. So that's pretty much it. Now we can just go ahead and plug in t at 4 pi over 3 and see what we get. So if we do that, we're left with the square root of, for our numerator, we have negative 4 over 5, and cosine at 4 pi over 3 is negative 1/2 squared plus negative 4 over 5 times negative square root of 3 over 2 squared. And in my denominator, I'm left with negative 4 times negative square root of 3 over 2 squared plus 4 times cosine at 4 pi over 3 is negative 1/2 times negative 1/2 squared plus 9. It's a lot of fraction work, but it's not so bad because you end up getting a common denominator. We're left with 4 over 25 plus 12 over 25 divided by 12 plus 4 plus 9, all under a square root, right? They both have square roots. So we're left with the square root of 16 over 25 divided by 25, 4 over 5 divided by 5, which is just 4 over 25. The next one's not so bad. I think you can do it without much more of my help, so I don't make the video too long. The only thing I will point out is that you have 3 different formulas. Which one do you use? Well, it depends on what you're given. Notice that we're given a function, so it might be beneficial to use that third rule. So for this one, You want to start off by finding f prime of x, then f double prime of x, and use chain rule. Don't forget that. Let me help you out. F prime is 1/2 times 4x minus x squared at negative 1/2 raised to negative 1/2 power and 4 minus 2x. If you're a bit confused how that happened, remember that chain rule. So you take derivative, think of this as 4x minus x squared raised to the 1/2 power. You bring down your exponent, you subtract 1, so you get that negative 1/2, and then you take the derivative of the inside. All right, and then to find the double derivative, you have product rule along with chain rule all over again. So the double derivative, or f double prime, is negative 1 times 4x minus x squared raised to the negative 1/2 power plus negative 1/2 2 minus x of 4x minus x squared of negative 3 and 4 minus 2x. Now that we established f prime and f double prime, we can go ahead and use our formula. So your formula says you have f double prime divided by 1 plus fy prime squared raised to the 3 over 2. Actually, I would clean this up before I even went there. Let's just do it. We're almost there anyways. Okay, so if we clean this up, let's write our negative exponents as 3 over 2 as denominators, so that we have negative 1 divided by 4x minus x squared raised to the 1/2 minus 2 minus x, 2 minus x, and 4x minus x squared of 3 over 2. Okay, then I want to get like denominators. So that we have a negative 4x minus x squared minus 2x minus x. We have 2 of them, so we write square all over 4x minus x squared of 3 over 2. Okay, let's go ahead and expand and combine like terms. We're left with negative 4x plus x squared minus 4 plus 4x minus x squared. And we're left with, well, my x squared is add to make 0, my 4x's add to make 0. We're just left with negative 4 divided by 4x minus x squared raised to the 3 over 2. All right, all of that was just cleaning up our double derivative. So that's why double prime, or f double prime. Now we can go ahead and apply our formula k. K is equal to y double prime of 1 plus y prime squared raised to 3 over 2. Okay, so y double prime is negative 4 divided by 4x minus x raised to 3 over 2. Our denominator have 1 plus 2 minus x, 4x minus x squared raised to negative 1/2 power. all of which is squared raised to the 3 over 2. And remember, you want to evaluate when x equals 2. So you plug in the 2, you work it out. You should end up with 1/2. That one was challenging. All right, let's continue with the normal and binormal vectors. We have seen the derivative r prime of t of a vector valued function is the tangent vector to its curve defined at rt. And the unit tangent vector t of t can be calculated by dividing r prime of t by its magnitude. When studying the motion of 3 dimensions, 2 other vectors are useful when describing motion of a particle along the path of space: the principal unit normal vector and the binormal vector. Definition of normal and binormal vectors. Binormal, not binomial. Let C be a 3-dimensional smooth curve represented by R over an open interval I. If t prime of t does not equal 0, then the principal unit vector at t is defined to be n of t equals t prime of t divided by the magnitude of t prime of t. The binormal vector of t is defined as b of t cross n of t, where t is the tangent vector. Example: for the vector valued function, find the principal unit normal vector, then if possible, find the binormal vector. Okay, so to begin, to find the normal vector, we have that here. We have n prime, or n of t, is equal to t prime of t divided by t prime of t, the magnitude of t prime of t. But this is not our tangent vector, so we need to find that first. So you first need to find t of t, which is made up of r prime of t divided by the magnitude of r prime of t. So we find that first, and then we can go ahead and apply the unit normal vector, the binormal vector after that. Okay, so let's start off by, and then the binormal vector. Binormal vector is b of t is equal to t prime of t cross product n of t. Okay, let's begin by finding t of t. All right, well, r prime is -4 sine of t, I minus 4 cosine of tj, divided by the square root of -4 sine of t squared plus -4 cosine of t squared. And that gives us -4 sine of ti plus -4 cosine of tj. Divided by the square root of 16 sine squared of t plus 16 cosine squared of t. That gives us negative 4 sine of ti minus 4 cosine of tj divided by the square root of 16, which is just 4. So in return, t of r, or t of t, as I labeled it, or in terms of t, so I wrote t, okay. T is equal to negative sine t of I minus cosine of tj. That's this first one. Cool. Let's take the derivative. T prime of t is equal to negative cosine of ti plus sine of tj. Okay, let's find n of t. N of t is defined as t prime of t over the magnitude of t prime of t. So we get negative cosine ti plus sine tj divided by the square root of negative cosine of t squared plus sine of t squared, which that will give us 1 by Pythagorean identity. So I have negative cosine of ti plus sine of tj, so that we get negative cosine of ti plus I sine of tj. Okay, lastly, to find the binormal vector, notice that the unit tangent vector and the principal unit normal vector are orthogonal to each other for all values t. So n of t dot product, or t of t, and then n of t, which is negative sine of t, negative cosine of t, which we found above, and negative cosine of t and sine of t, which we just found, we get 0 if we do the dot product. Furthermore, the principal unit normal vector towards the center of the circle from every point on the circle. Since r of prime defines a curve on 2 dimensions, we cannot calculate the binormal vector. So if we have a circle, I'll do my best job at drawing what's going on. We have our tangent vector, and then we have our normal and binormal, so that they go something like that. Actually, we have that right below. For any smooth curve on 3 dimensions that's defined by a normal value function, we now have formulas for the unit tangent vector t and the unit normal vector n, and the binormal vector b. The unit normal vector and the binormal vector from a plane that is perpendicular to the curve at any point on the curve, called the normal plane. In addition, these 3 vectors form a frame of reference in 3-dimensional space called the finite frame of reference, also called the T and B frame. Let the plane be determined by the vector t and n in forms of oscillating plane of C at any point P on the curve. So here it shows the vectors we just learned of. So last section we learned the tangent vector, this section we learned about the normal and binormal and how they behave. So because we had a circle, the binomial vector was always pointing inside, but that can change and it will vary based on the figure we're drawing. Suppose from a circle on the oscillating plane of C at point P on a curve. Assume that the circle has the same curvature as a curve does at point P, and let the circle have a radius r. Then the curvature of the circle is given by 1 over r. We call r the radius curvature of the curve, and it's equal to the reciprocal of the curve of the reciprocal of the curvature. If the circle lies on the concave side of the curve, it is tangent to the curve at point P. Then this circle is called the isolating circle of C at P. Find the equation of the isolating circle in 2 dimensions. We need to find only the center and the radius of the circle. Find the equation of the oscillating circle of the helix defined by y equals x cubed minus 3x plus 1 at x equals 1. Okay, well, to do this, we're going to use our formula f double prime of k, or in this case x, of 1 plus f prime of x squared raised to 3 over 2 power. So we need to find f prime and f double prime. Luckily, it's not so bad. Y prime is 3x squared minus 3. Y double prime is 6x. Okay, let's plug that into our formula so that we have 6x over 1 plus 3x squared minus 3 squared raised to the 3 over 2. Okay, so we want to plug in when x is equal to 1, right? That's what we're told. If we plug it in for 1, we get that our k is equal to 6. Okay, well, to find our radius r, that'd be 1 over k. So we have 1 over 6. So we're saying at x equals 1, well, here we have, if we just look at it this way, from this point of view, though it says it's a helix, which is like a spiral like this. From our perspective, using y and x only, it's a polynomial, right? We have a polynomial with 3 zeros. So when x is equal to 1, let's find that point. If I plug in 1, I'll get the coordinate point 1 comma negative 1. Okay, so if I have I have 1, 1, negative 1. I have this point here. So I have this polynomial function, and that's my curve. That's my 1 right here. And I have a circle happening at that point in my polynomial function. And that's not drawn to scale, I'm not too sure how deep it is, but I know my radius is 1/6. So if I look closer, we think about it, this is telling me that I have a center, and that's 1/6, and here I have the point 1, negative 1. So if I move up a point, if I move up 1/6 of a point, so meaning 1, and then negative 1 plus 1/6, that gives me my center. And remember, to find the equation of a circle, you just need your center and your radius. So therefore, we can say that our center is 1 and negative 5 over 6. And I have everything to label my equation. So my center and my radius. So recall your equation of a circle, x minus h squared plus y minus k squared equals r squared. So our answer is x minus 1 squared plus y plus 5 over 6 squared equals 1 over 36. There we have it. That was section 3.3, arc length and curvature. Thank you.